maybe you have done an infinite square well, but now we're going to do an infinite square well with a step. And I'm going to use the shooting method in Python. I kind of feel like that's one that people kind of like grok in their head the best. So we want to find the wave functions that work in here. And I want to start over, since we're using a slightly different differential equation. I want to go right back here to the original time-dependent Schrodinger equation. So where psi is a function of time and position. And remember what we did, right? We assumed that psi as a function of x and time can be written as f as a function of time multiplied by psi as a function of x. If I put that in here, then this function, when I take the partial with respect to time, the x comes out, so I get I h bar psi partial of f with respect to t. Over here, I take the partial with respect to position, so the time thing comes out, negative h bar squared over 2mf second partial of psi with respect to x. And then here I have plus u, the potential f psi. What we did was a trick to divide both sides by psi times f. And if I do that, over here the psi cancels and I get I h bar 1 over f partial of f with respect to t. Here the f cancels, equals negative h bar squared over 2m 1 over psi partial of psi with respect to x. And then I had, they both cancel right there. And we get back to the same situation we had before. This only depends on time. If I'm going to put a big if u only depends on space, no time dependency, then this whole thing only depends on position. And the only way for this differential equation to work, if this only depends on time and this only depends on space, is that they both are only equal to a constant, and we call that constant E. So before we did this, we had the differential equation without the U, and I just wanted to show you that we can put that U in there. U can go in there. So if I'm not worried about the time part, because that's easy to solve. But let's just rewrite this part, and it would be this negative h bar squared over 2m second partial of psi with respect to x plus u equals, oh, and I had 1 over psi, right? So this was, I forgot the 1 over psi. And it goes like this. Yeah, because look. No, it doesn't. That's just 1 over psi. See, good thing I... Rant, there. Okay, now I subtract u from both sides and multiply by psi, and I get this differential equation. Negative h bar squared over 2m second partial with respect to x equals e minus u times psi. I multiply by psi too. And so before, what we did with the infinite square well with no step, u was equal to, there was just no u. And now we have a minus u there. So how do we solve this equation? Well, what we're going to do is to use the shooting method. And the idea is I'm going to pick a value for e. I'm going to use the Euler method to find my psi function. And then if it meets the boundary conditions, that's fine. So we still have the same boundary conditions that right here and right there, psi of a equals 0, psi of 0 equals 0. And there's my step. And I want some function that looks like maybe this. It should go down right there. But I have to do that. And now I can model the motion, the position of this by calculating each point in the future and then keep adjusting E until we meet this boundary condition. So how do we do that? Well, the first thing we do is we solve this for, I'm going to write psi double prime. Psi double prime is the second derivative. It's going to be equal to negative 2m over h bar squared E minus u psi. And then I can use this to update psi prime. If we define psi double prime as delta psi prime delta x, then the psi prime at the end of this delta x interval, psi prime 2 is psi prime 1 plus psi double prime delta x. And then I can say psi prime equals delta psi delta x, and that's a psi. And I can do the same thing. Psi 2 equals psi 1 plus psi prime delta x, where that's technically psi prime 2. So here's my steps. Number 1, calculate psi double prime from the equation. And I need to know my value of psi. Notice that. Number 2, update psi prime. Again, I need to know this. I need a value for psi prime. I need to know what it is to begin with. So I'm going to have to pick that. Number 3, use that to update psi. And I can do that and step all the way over to here. And if I end up like this, which I probably will, then my final psi is too high. I increase my energy until I get there. And this is called the shooting method because we solve the differential equation and then we adjust it till it gets down here. And I'm going to start from scratch in the differential equation and then we'll animate it and it'll be cool. But let's just start it manually. How's that sound? Okay, so we want to do this. And I did do this before for the infinite square well in a little bit more detail. I'll link to that video down below if this was like, whoa, he went too fast. I did, because I want to do the coding. Okay, let's jump over here to Python. I already made a graph. Notice that. Is that big enough? A little bit bigger. That's better. Okay, let's put down our constants. H bar equals 1, M equals 1, A equals 1. Just to make things easier, you can always change those later. The other thing, I know that in an infinite square well, with these values, my lowest energy level is like 4.9 something. So I'm going to make my potential higher than that to make things interesting. You could make it lower, but I'm going to make it higher. I'm going to make it 10. So I'm going to say U0 equals 10. Okay, let's just go ahead and start calculating stuff. I'm going to want to do one Euler calculation. To do that, I need to start off, like I said, with psi, and I need to start with psi prime, which I'm called d psi, just because it's easier to write. At x equals 0. So I'm going to start at x equals 0. I need a dx, which is my step size. Let's put that 0.01. I need my initial psi equals 0. My initial psi, my slope, d psi equals 1. I'm just going to pick 1. It can be anything. I mean, it can't be 0. You'll get a trivial solution. And I need to pick my energy, E equals 0. That's the start. Now I can go ahead and do my calculation. So I'm going to move all the way across that well until I get to the other side. And then I want to see what my final function is. So I'm going to move x while x is less than a. Number 1, calculate psi double prime. I'm going to call that dd psi equals. And I'm looking at my equation over here. dd psi is -2 times m times divided, well, yeah, I'll just put it all together, times e minus u times psi divided by h bar squared. Now there's a problem. I don't have a value for u. So I need to add that in there. The value of u is either going to be 0 or u0, depending on my x value. So I can just make that an if function. If x is greater than a over 2, then u equals u0. Else, u equals 0. So when I move along that calculation, it's going to check. Am I greater than a over 2? Then I put that as my u. If not, it's 0. So now I can calculate that down there. And you can't even see that. I'm so dumb. You almost could. Right there. Now we both can't see. There we go. So there's my double, I think you saw it before I typed it. Now that I know the second derivative, I can update the first derivative. D psi equals d psi plus double d psi times dx. That updates my first derivative of psi. Now I can update my value of psi. Psi equals psi plus d psi dx. Now I need to move x. X equals x plus dx. I want that bigger. I like big. Okay. And that's it. That should run through the whole thing. Now I do want to make a graph just so we can see it, and I'm going, and I don't need to print the energy. I know what the energy is. It's 0. Let's plot this data point, f1.plot x psi, and run it. What do you think? Think you'll run? There. So it worked. It blew up. It did not get down to 0. So let's just change the energy. Let's increase the energy. Notice right here, this value, the final value is 3.51. If I increase my energy to, let's say, 2, I'm just picking a value here, and I run it again, now I'm at 2.4. So I'm lower. If I keep increasing my energy, I should get down to the point where this is down over here. That's what I want. But we're going to just animate that. I should save this. Shooting stepwell. I'll give you a link to the code down below because, you know, I like to share. Okay, so what I'm going to do now is just start with E equals 0. And I'm going to increase the energy, dE, by 0.01. And then, so I can run it. I can see if my psi is great enough. If it's greater than 0, if it is, increase energy and do it again. So let's pick a value. I'm going to make this psi final equals 1 because I want to run this and see if my final psi is greater than 0. So I need to start with the value of psi, and I did this before. And then I can make a loop while psi final is greater than 0, because I'm going to keep increasing it until the energy, the function goes below that. While it's greater than 0, let's do an animation. So rate 100. I'll make it 200. And now I'm going to do that whole loop again. But if I want to do that loop again, I need to reset all my values. So I need to reset x equals 0, psi equals 0, d psi equals 1. And then this is, and I'm also going to make an animated graph. So let's make a function called f data equals an empty list, and then I'm going to indent all of this because it's part of the loop, and I'm not going to plot. I'm going to add to my data f data equals f data plus my x value, which is x. Oh, I'm going to need it like this. X and my psi value, which is psi. And after that loop, I'm going to plot my data. f1.data equals f data, and I need to set my value for psi final. Psi final equals psi. Right? Whatever I ended up with, that's my psi. And then I'm going to increase my value of my energy. E equals E plus dE. That seems too easy, but I think that should work. Let's just see if it works. What do you think? Okay, increasing, looking good, looking good. Okay, so there you go. Now you notice it does indeed meet my boundary conditions. It's not symmetrical like before. Remember, we would have a sine function in the other case, but here it just kind of like exponentially decays. And that's because our energy is lower than that step size. Now let's go ahead. I didn't print out the energy. I should do that. Let's print out the energy at the end. Print E equals E. And the units don't really matter because I'm not really using real units anyway. Okay, now I gotta watch the whole thing again. It is kind of cool to watch though. And I could put a line there where the potential is. I think I might do that. I don't know. 8.85. So you'll notice that it's a higher energy than before. Now I do want to do one thing. It's a higher energy than without the step. I want to find the expectation value for x. And in order to do that, I actually have to normalize. I'm going to have to normalize my function too, because it's not normalized. So let's normalize the function and plot it. And then we'll calculate the expectation value. I'm just trying to think. I could do that. Let's do that. Let's do this. I'm going to, so I get done with this whole process, right? And I have a value of e. What I'm going to do is, I'm not going to plot it this time. I'm just going to run it without plotting, get my final value of e, run it again and get the data so I can make a function that I can integrate. So no plotting. All I have to do is comment that out. If you want to, that's fine. So now I have my e. What I'm going to do here is just recalculate everything again. X equals 0. I know the e value, so I know it works. Psi equals 0. D psi equals 1. While x less than a, I just need to copy this whole thing. Copy. I'm going to do it again. And I'm not even going to, although that's not right, tab, tab, D tab, D tab, D tab, D tab. Okay, that's better. Now, what I want to do is to take my values of psi and my values of x and add them to lists so that I can deal with them. I'm going to call this psi p for my plotting list and xp for my plotting list. And I can just add my values to that list. So down here, xp equals xp plus x, psi p equals psi p plus psi. And now I'm going to have a list. I'm going to have two lists with my x's and y's, and I can normalize it. So to normalize it, I'm going to integrate psi star psi over the whole region. And I'm going to do this in a little bit of a cheat way, but it should be fine. So at the end of this, I'll have my values. And you'll notice that here I have my e. So it should give me the right answer. Let's integrate this. I'm going to say I equals 0. I is my integral. I need to calculate what that is. And once I do that, I can divide my function by that I, by the square root of I, and that will be my normalization concept. So while, for I in range length of xp. So this goes through every item in xp with the index I. And I can use that. I don't actually need, I don't actually need that. I can just do this. For t psi in psi p, and that goes through each one in the list, I equals I plus t psi squared times dx. Right? So I'm doing psi star psi dx, so I need to take the length of that is psi star psi, the width is dx, and that's going to be the little area of that box and add it to the total, and that'll be it. That's my I. Then, once I have I, a, the term in front of the psi, is going to be 1 over the square root of I. So I can use that. Now, let's plot. Now I'm going to plot psi. And this will be normalized. Let's plot psi star psi. So I should change this up here. This is psi star psi. And down here, I'm going to plot it. And I need my a. It's going to be a squared. But for I in range length of xp, I do need the range in this case because I have two different lists. I need the x list and the psi list. I'm just going to plot. f1.plot. My x coordinate is going to be xpi. No, I. My y coordinate is going to be a squared times psi pi squared. That's it. It should plot the normalized, the normalized probability density. And it didn't. Why not? E. It didn't do anything. It should have at least done this. Oh, it did that. And then it did this. It didn't even print the E. It never got down there. Oh, dear. Let's print E up here. Let's just see. I must have made a mistake somewhere. It didn't give me an error, though. Whoa. Well, that's weird. That's scary. Oh, it's in an infinite loop, looks like. While size greater than 0. Oh, this is why. It was going through that slow, and then it just wasn't showing anything because I never plotted it. Okay, so this shows you that the probability of finding it's much closer to the left than to the right, right? You're more likely to find it over here. It's probably not going to be in the well. That's kind of cool. We could integrate and find the expectation value for x, but I don't want to do that. I want to do one more thing. What if the energy is greater than E? I guess I got to go back and find the next energy level, which I shouldn't have turned that off. Well, I'm going to tell you the short end of the story, and this was your homework. Find the energy level that is higher than the potential step, and where do you think you're more likely to find the particle? On the left side where there's no step, or on the right side where there is a step? And if you want to even calculate the expectation value, that'd be a double thumbs up for me, and that'd be a pretty cool idea. Okay, so there you go. Shooting method with a non-flat infinite square well. Still an infinite square well, but it's got a bump, a step. The end.